Hello. Before I present the rules which are essential for completing the square, I would like to briefly go through the computational rules for real numbers. You are probably very familiar with these rules, but, well, we just have to start somewhere. So the title is Computation Rules for Real Numbers, and these are the rules you probably recognize: the commutative law for both addition and multiplication, the associative law, distributive law, the neutral element for addition and for multiplication. So the neutral element means that if you add a 0 to any number, you just get back the same number, and if you multiply any number by 1, you just get the same number unchanged as the result. And the inverse element, so the additive inverse is called the opposite or negative a, and the inverse is often denoted as a to the power minus 1, or simply 1 divided by a as a fraction. And such an inverse element for multiplicity for multiplication is only exists for numbers which are different from 0, of course. And you have probably seen in your earlier education illustrations like this, which just show you how to understand these rules. And here in these pictures I just made illustrations for the rules for natural numbers, because otherwise it would be difficult to illustrate. So if you look at natural numbers as on number of elements in some set, simply a number of some objects, then you understand that addition is commutative, because it doesn't matter if you first count the objects in the first group and then in the other, and put them together on the other way around. And commutative law for multiplication can be best illustrated as with help of areas of rectangles. So it doesn't matter if you count width times height or the other way around, you will get the same area. Of course, if you work with the same rectangle in both cases, which is the case here. So you see that this rectangle is simply this one rotated. And the associative law tells you that you can group elements as you like. So you can group terms for addition or factors for multiplication. And the illustration would be for addition: if you have 3 groups of elements, one with m element, the second one with n elements, and the third one with k elements, then if you count all the objects together in the 3 groups, then it doesn't matter if you first put together the elements in group 2 and 3 and then add this number to the number of elements in the group 1, or you put together the first 2 groups and then add the number of the elements in the third one. It's the same result. And associative law for multiplication can be illustrated with volumes. And the distributive law, which will be the most important for us in the context of computing the square, tells you that you can perform such an operation if you have a product of one element with a sum of 2 other elements. Then you can compute this product in this way, that you multiply both terms in the parentheses by the factor standing before the parentheses, and you add together the 2 obtained products. And here is an illustration of this law, again just for positive natural numbers. You see, you can again think about areas. If the left-hand side corresponds to the area of the rectangle with height k and width or length m plus n. You see? So the area will be k times m plus n, right? But if you divide this rectangle in 2 rectangles, as you see here, one with size m times k and the second one n times k, then the total area will be, of course, equal to the sum of these two areas. And this is exactly the right-hand side of this formula. So these are just illustrations, and later in your education you will discover that these rules does not need to be justified in any way, because they are axioms, and axioms are truth which are just accepted without any need for proofs. And more about it will be discussed, or is discussed, in this course Pre-Calculus 1 Basic Notions. So if you are curious about this stuff, please have a look at this course. And another property which is very important is the so-called zero product property, which is quite simple, and I'm sure you have applied this many times. It simply tells you that if a product of some factors is equal to 0, then at least one of the factors must be equal to 0. And this zero product property is used for solving equations. So, for example, if you are familiar with polynomials, then you know very well that in order to solve a polynomial equation, some polynomial is equal to 0, well, you need to factor this polynomial in linear terms, if possible, of course, because not all polynomials will be possible to factor in linear terms, but this one is. You can verify that this polynomial is equal to this product. Then, of course, this product is equal to 0 if one of the factors is equal to 0, and this is if x is equal to 1 or x is equal to -2. And now, the last and very important thing in this video: you must respect the equality sign. What does it mean to respect the equality sign? It means that if you have an equality, then the things which are standing at both sides of the equality sign must be equal to each other. But still, we will do strange things to equality sign, and I will show you two examples. The first one will be very well known. You have done it many times. So you see, if you solve an equation of this type, you can do a pretty funny thing here. You can subtract 2 from both sides. It's kind of zero operation. Nothing happened here, right? Because if 2 sides are equal to each other, then they will remain equal to each other if you subtract the same number from them, right? So it's a kind of zero operation. You didn't change anything. But actually you have changed a lot, because by subtracting 2 from the left-hand side, you have separated x, and you just get your solution to this equation. You get that x plus 0 is equal to 7 minus 2, which is 5. So in this way, but by performing this kind of ridiculous zero operation, you solved your equation. And observe, very important, you are not allowed to subtract a number just from one side, because then you would disrespect the equality sign. You must perform the same operation on both sides to be good, to be still able to keep this equality sign. And now the second case, which will be probably new to you. And here you will see a glimpse into completing the square. You see, if you have such an expression, it's a polynomial of second degree, you see you have x squared here, you can rewrite it in the following way. You can add 1 and subtract 1 to the expression. Again, a zero operation. It has nothing, it hasn't changed anything. You see, you have simply added 0 to your expression. But actually it did change a lot, because as you will see in video number 4, this expression here is equal to x plus 1 all squared. And you have actually just completed the square for the first time. Don't worry if you don't understand this step, this will be thoroughly explained in video number 4. So what have we got here? We got that this expression here is equal to x plus 1 all squared minus 4, because, well, minus 1 minus 3 is just minus 4. And by this, you see that if you must solve the equation that this expression is equal to 0, it would be the same as solving equation that this expression, which is the same, is equal to 0. But this is equal to 0 if x plus 1 all squared is equal to 4, right? By the way, this symbol stands for equivalence, or it reads if and only if, and it's often abbreviated into IFF, if and only if. So now we see that this equation is equivalent to this one. And this one is easy to solve, because you know that a square of some number is equal to 4 only if this very number is equal to 2 or minus 2. And then you see that x itself must be 1 in the first case or minus 3 in the second one. So you see why it was interesting for you to add and subtract 1 from this expression to complete the square. And you completed the square in order to be able to solve this equation. So now you have seen some basics, and you have seen already a kind of how the method will look, but you don't know all the details yet, and don't worry, they will come later. Thank you for watching. Bye bye.